Hi folks, welcome back to Physics with Captain Rod. I'm here to help you with this dandy here that we're looking at. Number 35, the object shown is a pair of 100 kilogram, 1.4 meter bars. Okay, the system is supported as shown and free to rotate. All right, the moment of inertia of this system is going to be important. So start by calculating that. Now for this bar right here, the moment of inertia is just 1/3 ml squared. For this bar, again, about this axis, use the parallel axis theorem. It's 1/12 omega or 1/12 ml squared about its centroidal axis plus ml squared tacked on for the fact that the axis has moved. So I would start by calculating the moment of inertia of this object. Get this down to a number in kilogram meter squared. Okay, now imagine it's displaced from equilibrium. I'm going to kind of exaggerate the displacement here, right, in angle theta. You need an expression for the potential and kinetic energies. Now, the kinetic energy is no problem. The kinetic energy is 1/2 I omega squared. So in this problem, that would look like 1/2. The I is a number that you have. And omega, another way to write that is theta dot squared. Okay. Now, as far as this object is concerned, treat it like two different bars with two different center of masses. This thing has a potential energy of minus mg L/2 cosine theta, because this distance from here to here is L/2 cosine theta. For this object right here, your potential energy is minus mg L cosine theta. And these can be just added together pretty easily. I'll let you do that. So what you do is you write out an equation that looks like this. Your total energy equals your potential energy plus your kinetic energy. And for the potential energy, it's the sum of these two. And for the kinetic energy, it's this. Then you hit it with the time derivative hammer. And for the total energy, now again, the total energy isn't changing. Nobody's adding energy to or taking energy away from the system. All that's happening is potential and kinetic are kind of trading places. So this time derivative is going to be 0. This thing is going to give you something, and I think you're going to end up with sine theta, maybe a cosine theta, and a theta dot, I think. I don't know. I'm not sure what. I'm not working this all out in my head here, so don't quote me on all of this. But these are all the things that could possibly show up in that equation, okay? After you differentiate it, sines become thetas, cosine thetas become 1, right? When you differentiate this term, you're going to get something times, it's going to have a theta dot and a theta double dot almost certainly. And the theta dots are going to cancel. So again, when you get this whole mess done, anywhere where you got a sine theta, put theta. Anywhere where you see a cosine theta, put 1. And then write it theta double dot plus a number times theta equals 0. Okay. Now this is going to have solution of theta equals a sine omega t plus b cosine omega t. Now in this problem, at t equals 0, the theta dot is 0 because this is an example where somebody plucked it from equilibrium and let it go. If you apply this condition, I believe you are going to end up throwing away, let me think about that. I think you're going to throw this term away. Okay. Then hit this with 2 time derivatives. Sub it here. Take this, sub it here. and you're going to be able to get the angular frequency out of it. You should be able to get a number out of that at that point. And then use the condition that when theta is some number given in the problem when t equals 0 to get that thing. Okay, so that problem is quite a bit of work. Hope you're having fun with it. Have a great day.